Here we're looking at another example. Okay, so notice that if we start at the atoms bonded to the vinyl carbon on the left, the first two atoms are both carbons. They both have the atomic number 6, and there is no difference. If you look at the next atom out, highlighted in blue, we have that the atoms that were bonded to the green carbon are carbon, hydrogen, and hydrogen, and the atoms bonded to the green carbon that is on the bottom are that the green carbon has carbon, hydrogen, and hydrogen bonded to it. And so the atomic number of the atoms, the highest atomic number is carbon, but carbon is identical to carbon, so there's no difference. So then we go one more atom out, and this is where we get interesting. What we say is that the blue carbon has 3 bonds to carbon. So let's get a highlighter. So these carbons here correspond to this carbon. This is what is bonded to the green carbon in yellow. What is in yellow is bonded to the green carbon. Okay, so I'm going to write in purple pen the atoms that are bonded. How about in blue pen, I'm going to write the atoms that are bonded to the blue carbon. And on the bottom, the blue carbon has a triple bond. So we're going to say it has 3 bonds to carbon. And that's CCC. On the top, the blue carbon has 1 bond to oxygen, 1 bond to hydrogen, and a second bond to hydrogen. The highest atomic number atom is oxygen. It has a higher atomic number than carbon. The number of carbons that it bonded to in this case is not relevant because there is one atom that has a higher atomic number in the top. So now we know that our top group is our high priority and our bottom group is our low priority. If you look at the vinyl carbon on the right, at the first atom out, we have carbon and carbon as our highest atomic number. And the atoms, so we have C and C for our green. Both of these have an atomic number of 6, and so they are equal. If we go out to the blue carbon and we look at the atoms that are bonded to the green carbon. Bonded to the green carbon, we have carbon. I meant to do that with a pen. Pen. And green ink. Okay, bonded to the green carbon is carbon and hydrogen and carbon. So because it's a double bond, we're going to say the green carbon has 2 bonds to carbon and 1 bond to hydrogen. That is, if I can draw in a hydrogen on the skeletal structure, but I shouldn't have to. I know it's there. Okay, so looking at the green carbon on the bottom, it is bonded to carbon, which is blue, and the green carbon is a CH2 group, so it has also 2 hydrogens. Now we've reached the end of the molecule, and the highest atomic number that the green carbon is bonded to is 6. Those are equal. So now we have to add a new rule. If at the end of the chain or at the end of the molecule, the groups you are comparing, there is no difference in atom with the highest atomic number. The group that is the highest priority will be chosen by the highest number of atoms with the highest atomic number. So only after we can say, okay, 6 is equal to 6 for the atomic number of carbon, can we say, I can't go any to the next atom out. Those are all hydrogens. The blue carbons are only bonded to hydrogen. Hydrogen is equal to hydrogen. So all we can do at this point is to look at how many of the 6 carbon high atomic numbers I have bonded to that one carbon. And so we can say that having 2 carbons of atomic number 6 is better than having 1 carbon of atomic number 6. Because we're not going to have an atom of higher atomic number. We can see that there's no heteroatom. So we're going to label the top group as high and the bottom group as low. And then we can state clearly that this is a Z isomer. Okay. The trans isomer has the same groups, and so we've already determined which group has the highest priority, and we don't need to look at that for the Z isomer. We would go through the same conclusions. All right. Now, here's another example where they throw in something different. What we have here is what I talked about on the first chapter. We have a deuterium atom, and I told you guys that the deuterium atom is heavy hydrogen, or hydrogen with a mass number of 2. But for our purposes, in organic chemistry, they always write D instead of the formal isotopic label of mass number of 2 hydrogen, atomic number of 1. So this is equal, and you just have to remember, it's up to you to remember that deuterium is heavy hydrogen. Okay? So you might ask, why would you want to have an isotope rather than a normal hydrogen bonded to the molecule? Well, the purpose of isotopic labels such as deuterium 18O, 15N, and 13C is to change the mass of the molecule above what you would see if deuterium was not present. This change of mass can be used to identify a molecule and to identify steps in a molecular synthesis based on how these isotopes are added or lost. And we do this using a mass spectrometer, which measures the mass of molecules that go through it. Okay, so here we have on the left final carbon, and I'm going to look at the skeletal structure. I want you guys to get used to looking at the skeletal structure. So we have the skeletal structure and the final carbon at the left. Oh, did I forget to draw the double bond? Tisk. All right, looking at the left final carbon, we have the first atom out is hydrogen or deuterium. Now, another rule. If the atoms you are comparing have the same atomic number, they're isotopes, but they're not the same thing, you will compare atomic mass, or the mass number. So we're going to choose deuterium as our high priority group because it has a higher mass number. Looking at the other side, the final carbon on the right, First carbon out, first atom out in green is carbon. Carbon equals carbon. We can't decide. Go one more atom out, and we have that carbon equals carbon. Okay. So in this case, we are going to choose the higher priority group once we get to the green carbon as that this double bond is going to have a higher priority than these single bonds. Yeah. All right, so look at the other one. We have our two green carbons. They're equal. They both have the atomic number of 6. Going one further out, we have the blue carbons. They're equal. They have the atomic number of 6. But what are those blue carbons bonded to? They've written that out for us, but I want to point it out myself. So the blue carbon on the left is a methyl group. So it is bonded to 3 hydrogens. It's bonded to H, H, H. The blue carbon below is a CH2 group. It's bonded to 2 hydrogens. And then this is where you might get tricky. This blue carbon is also bonded to this green carbon. We have to count. It's actually bonded to the green carbon twice, right? And what you do, because it's a double bond, I can also say that the blue carbon above is bonded to a green carbon. So if I write out all 4 bonds that the blue carbon has, on the top I'm bonded to carbon, hydrogen, and hydrogen. And if I write out all 4 bonds that the blue carbon on the bottom has, the one in the double bond, I have carbon, carbon, and hydrogen. Why do I write carbon twice? Because it's a double bond. So now, if we erase 1 carbon for each set, then my conclusions of HHH and CHH matches the technique shown to you by the text when you read the text that gives HHH for the top blue carbon and HHC for the bottom blue carbon. So this has to do with the fact that it's a double bond, and we can say that the bottom group has a higher priority because that carbon has an additional bond to carbon that the blue carbon on the top does not have. So that is the Z isomer. Okay, so let's practice naming, okay? So here we have a molecule that I've drawn for you, and the first step that we're going to do is to number the longest chain. So what is the longest chain? I'm going to start at a carbon that is closest to a substituent. 1, 2, and we also want to pick the chain that has the largest number of substituents. 3, 4. So I've labeled my chain. I have 4 carbons. And it's got a double bond, so the suffix is going to be butene. And I'm going to call it a 1-butene because the first vinyl carbon in the chain is at carbon 1. The first sp2 carbon is at carbon 1, and so it's called 1-butene to tell you where the ene starts. Next, I've done the step of numbering the chain. Now we're going to write out the substituents with the carbon number the substituent is attached to and its prefix. So at C1, I have chlorine. At C2, I have ethyl. At C3, I have a methyl group. If I were to put these in alphabetical order, it would be chloroethylmethyl. So we're good. Next, we need to look at the double bond and determine the priority of the groups at each vinyl carbon, the right vinyl carbon and the left vinyl carbon. So I like to start at the left vinyl carbon. The left vinyl carbon is bonded to chlorine, and if I draw it in, it's bonded to hydrogen. If we compare chlorine and hydrogen, chlorine has a higher atomic number and is our higher priority group. Looking at the right vinyl carbon, highlighting in green, they have the highest atomic number atom is carbon. There's no difference. We need to move forward. What is carbon 3 bonded to? What is the green carbon below carbon 3 bonded to? And make a comparison. So this green carbon is bonded to carbon, carbon, and hydrogen, and the carbon below it is bonded to carbon, hydrogen, what? Okay. Yeah, this one. Okay, pen. Yes. So this, the green carbon highlighted below is bonded to carbon and 2 hydrogens. Okay, so in that case we have a difference. If we go out one atom further and we look at carbon 4 and the carbon below carbon 4, we have carbons that are each bonded to 3 hydrogens. That's no difference. So we get to the very end of the chain and we have HHH compared to HHH. That was not useful. So you go back and you say, I can't determine it based on highest atomic number. I need to determine this by highest number of atoms with highest atomic number. If we determine this by highest number of atoms with highest atomic number, then the top group is the high priority group. And the bottom group is the low priority group. So on one side, the high priority group is on the bottom, and on the other side, the high priority group is on the top. That means that this molecule has a configuration of E. Let's just circle it. So we are in E configuration. And then we can name it. E, 1 chloro, 2 ethyl, 3 methyl, 1 butene. Okay, moving on from double bonded molecules. We're going to look at chiral and achiral objects. A chiral object has a non-superimposable mirror image. The left hand compared to the right hand. These images are mirror images, but they are not superimposable. The left ear compared to the right ear. A car in England versus a car in America. They're mirror images. They're not superimposable. An achiral object has a superimposable mirror image. Think about when you were students in elementary school and your chairs were not attached to your desks. You could stack the chairs and move them out of the way. The chairs were superimposable. A fork that has a symmetric design would be superimposable. And a glass that has no writing on it would be superimposable. Chiral molecules. A chiral molecule has an asymmetric center. An asymmetric center is an atom that is attached to 4 different groups. Here we have an example. Central atom bonded to 4 different colored atoms. That is an asymmetric center. The example that we were studying in lab yesterday was 2-bromobutane, which looks like the molecule in red as a skeletal structure. In a skeletal structure, the asymmetric center will appear as a carbon that has 3 lines or 4 lines. If the 3 lines lead to 3 different groups, then it will be an asymmetric center, because the 4th group is the unseen hydrogen. When I am looking at this molecule, how am I comparing if the groups are different groups? I specifically choose only this carbon, and then I say, what is it bonded to? It's bonded to 1, bromine, 2, methyl, 3, ethyl, 4, hydrogen. I didn't write the same group twice, therefore it is an asymmetric center. If you were to build the molecule 2-bromobutane and then build its mirror image, the 2 molecules would not be superimposable. They would be unique.